I will share my screen to present our next speaker. That is Marta Del Zoppo, that will examine the assessment and retrofit of structures for natural hazard. Marta is a civil engineer with master's degree in building and architectural engineering from the University of Catania in Italy, and also has the PhD in phenomena and environmental risks for the University of Naples. She is the chair of the FIB Young Members Group, and board member of the International FIB Young Members Group, an active member of Commission 3, Task Group 3.2, modeling of structural performance of existing concrete structures, and 3.4, selection and implementation of interventions through life management activities and measures for concrete structures, a member of the Task Group 5.1, FRP reinforcement of concrete. So I will ask Marta to share her screen and maybe give her presentation now.
Many thanks, David, for your introduction. I hope you can see my screen properly. And good afternoon, everyone, and thank you to the FIB for this invitation. So today I will present this work that will focus on the assessment and retrofit of existing reinforced concrete structures for natural hazards. And a part of these results that will show has been developed during the SPOT project that was a national project in Italy about potentially triggerable offshore seismicity and tsunami. And this research has been further developed during these years thanks to our international collaboration with UK, Sri Lanka, and the University of Hawaii. So as we know, we are aware that our existing structures and infrastructures represent a great challenge for our generation as engineers, because these structures are usually designed according to obsolete standards and of course are not able to comply with modern safety levels. And we have also the use sometimes of poor quality construction practice, especially in some developing countries, deterioration due to aging problems and lack of maintenance. So these structures are very vulnerable to natural hazards in general. And so a performance assessment followed by preventive retrofit intervention can reduce the damage to such structures to under natural hazards. In general, natural hazards become disasters when there are human life losses. So if we look at the reports, the last reports of the United Nations Office for Disaster Risk Reduction, we will see that we are facing a significantly increase of frequency of natural disasters and related human losses and economic losses. And these numbers are almost doubled with respect to the previous one. So this is an increasing rate that is worrying. And also, if you look at the top 10 deadliest deadliest disasters of the last decade, we will see that there is a high frequency of earthquakes as the most destructive, and the more destructive in general is the 2004 earthquake and tsunami event that affected many countries in the Indian Ocean. So this one is one of these kind of sequential events are very, very dangerous. And the frequency of this kind of event is going to increase. The last example we have seen a few weeks ago in Turkey with the an earthquake, 6.6 magnitude earthquake followed by tsunami, I would say a coastal flooding with a maximum elevation of 1.9 meters. That kind of events are going to happen, and that our structures are not completely safe to that kind of such kind of events, because several losses occur during this disaster. And we live also in a historical period of fast changes caused by the climate changes, as the previous speakers were also saying. Climate changes are changing and are increasing the vulnerability of our structures and also the exposure to natural hazards because of the increasing rates of disasters or events like hurricanes, cyclones, storm surges, and tsunami. And the global warming that is causing sea level rise will, of course, increase also the risk of coastal flooding due to storm surges and tsunami. And this, combined with the increasing carbon dioxide concentration in our atmosphere, higher temperature, higher humidity, will also increase the rate of corrosion of our existing reinforced concrete structures, and so increase their vulnerability to, in general, to leaks. In addition to natural hazards, we need also to consider that we have many induced hazards. One of the most famous example is the Groningen gas field. But where is this phenomenon on induced seismicity in that area given by the gas extraction? But another example is about the potential induced seismicity and tsunami triggered by these earthquakes for activity, offshore activities near seismogenic faults. And this was the objective of the SPOT project in Italy, where several spot areas were identified along the Italian coast to these areas are potential at risk of earthquakes and tsunami due to the offshore activities. So in general, we need to define a life cycle procedure for assessment and retrofit of existing structures, looking for single and multiple hazards. And of course, during the assessment, we need to consider also the degradation of materials that can occur during the life cycle given by the corrosion, for instance, and a proper assessment of the behavior of the structure, the performance, and the damage will allow for good design of retrofit intervention, a prioritization of intervention when we talk in terms of risk perspective, and also to with the retrofit strategies needs to extend the service life of our structures. So also in this context, these are the two pillars that we need to consider: resilience and sustainability. So resilience of our communities to natural hazards this is a pillar, is paramount important guarantee that our communities, in terms, of course, we need to focus on the physical part of the community. Of course, we are looking at the perspective of buildings and structures. We need to guarantee that the community is able to recovery after the event. So actually, we need to avoid the damage and allow the full recovery of the activities in the shortest time as possible. And also we need also to consider the sustainability of the intervention. So if there's need to recover the original damaged buildings, we need to consider a sustainable approach. So the sustainability of materials adopted, and also the management of debris can become a real issue in such conditions. Among others hazards, the earthquakes are the most frequent, as we have seen from the United Nations report, and are the most dangerous also for the built environment, so for structures. But the major concern is that earthquakes can be a trigger for many others hazards, such as landslide, fault displacement, and also tsunami, that we have seen are the more destructive for both the built environment and also for human lives. And I will focus on these two in the next of this presentation. In particular, seismic hazard and earthquake engineering in general are very high developed and quite well understood nowadays, while the other kind of hazards are less investigated and can also represent the major threat for our communities, for our built environment. So in the field of seismic assessment, the experience that we acquired in the aftermath of previous earthquakes allow us to be aware about the critical deficiencies of our existing reinforced concrete structures during earthquakes, even of moderate intensity. In terms of damage to structural components, you know that the most critical parts are related to beam column joints, but also to the lack of detailing that is translated in a low shear capacity and in a limited ductility of beam and columns, among many other problems related to shear walls and other structural elements. Damage is also concentrated to non-structural components that are also the major cause of losses, economical losses after earthquakes of minor intensity. It can be a threat for human life, especially when we talk about cladding can overturn during earthquakes and then become a danger for human life. But so we know so many things about earthquakes and how the structure responds to such events, and we have also several tools and to predict with a good accuracy the behavior of structure when subjected to earthquakes. But what about tsunami? So when we talk about tsunami engineering, this is a quite brand new, relatively new field of research, and the knowledge about the behavior of structures under such kind of hazard is quite low. So when we approach to other kind of hazard different from earthquakes, we need to consider that the performance of structures can be completely different in fundamentals. So we need to start basically from the beginning. So tsunami are a sequence of waves and are given by characterized by the very long wavelength period, typically ranging between 20 and 40 minutes. And after the first phase of impulsive bore, we have tsunami flow is similar to a quasi-steady flow. And under this kind of quasi-steady and long duration loads, the behavior of structures is not dynamic. I mean, this kind of external loading does not excite the dynamic response of a structure, given the difference of fundamental periods. So the behavior and the performance of structures subjected to tsunami is static in nature, is monotonic under the inflow inundation, and is controlled by the lateral force given by the tsunami on the single structure and the single building. To understand more about the behavior and the performance of structures during a tsunami, we can start analyzing the effect induced by previous tsunami on structures. In general, tsunami are very complex phenomena that induce several kinds of loads and effects on structures. We have lateral loads given by hydrostatic and hydrodynamic pressure that may have higher magnitude at the lower stories of a building, and then loads cause failure modes in terms of mechanisms, like this one, development of plastic hinges at the of columns of the ground story level, but can also cause shear failures, like this one, locally on ground story columns, and of course the damage to measuring field walls and partitions. But tsunami also induce vertical loads in the form of uplift loads due to buoyancy of the closed space submerged in the fluid, because of course we are talking about this flow of water, seawater, and buildings that are impermeable or with very small open duration can be affected by the buoyancy on foundation caused by this big enclosed space inside the building. And this kind of effect can lead to failure mode like this one, a global overturning of the structure, especially in the case of when shallow foundations are adopted. And this was the failure mode typically observed in Japan during the 2011 Tohoku earthquake and tsunami, because of the traditional construction technique in Japan, where they use as structural components exterior claddings made by lightly reinforced concrete walls. So basically, the structures were like boxes, reinforced concrete boxes, submerged in the tsunami flow, and then they overturned in many circumstances. Other effects related to tsunami are also by the soil. This phenomenon is called scour, and this is a soil erosion below the foundation of the building, the local loss of support of the column, and so can be a trigger for partial collapse of the structure, and also the impact with floating debris. Several debris are transported by the seawater, especially near seaports, but in general, ship containers can be transported by the water and can cause several damage to structural elements, and also in this case lead to local failures. So based on the lessons learned from past mega tsunamis, a performance-based assessment methodology has been developed for such kind of hazard. Starting from an hazard map, of course, we can assess which kind of loads are acting on a structure, and then define which is the predominant failure mode for the building. Of course, in this assessment procedure, we need also to consider the effect of pre-existing damage due to corrosion, always looking at the entire life cycle of the structure, damage occurred by the preceding earthquakes, in the case that the tsunami is triggered by a previous seismic event, and also if there exists any kind of retrofit intervention that have been already applied on the structure to prevent seismic damage. On the next, I will focus on this structural typology that is very diffuse in the Mediterranean region, but also in many other many other countries in the world. Reinforced concrete frame structures with unconfined measuring fill walls. These kind of structures, when subjected to tsunami, are mainly, the response, the load transmission is governed by the exterior claddings that in this case are made by masonry infill walls. But under such kind of out-of-plane loads, so the lateral pressure induced by tsunami on these masonry infill walls will cause the out-of-plane failure of such systems. So this kind of walls is called tsunami breakaway walls, because they will collapse very soon during the tsunami inundation, allowing the water to pass inside the building. And for this kind of structural typology, we developed structural analysis methodology. So given the fundamental difference between tsunami engineering and earthquake engineering, we need specific structural analysis methodology to design and assess the performance of structures during such kind of hazard. And in the context of tsunami engineering, the main methodology is the variable depth pushover analysis, the VDPO analysis that has been developed by Petrone et al. In 2017 and is now adopted by the American Design Code for tsunami evacuation buildings. And this methodology has been further improved in recent years in our recent collaborations to include also the effect of breakaway infill walls and also the effect of uplift loads on structures. So basically, the variable depth pushover this new analysis for breakaway infill frames, so the VDPO BI analysis, is nonlinear static analysis, pushover, that considers step by step an incremental increase of tsunami inundation depth. And for the increase of inundation depth, we can see here some steps. By increasing the inundation depth, analysis will consider the progressive damage of non-structural components, so the failure of infill walls, for instance, under the lateral pressure of the tsunami, and will apply to structural elements, both vertical and also horizontal components of the structure, the actual distribution of loads caused by the tsunami. Okay, Now we see just an application of the DPO analysis, DPO BI analysis for a three-story frame. We want to assess the capacity of this structure, assuming that the tsunami demand at the building location is known. So we know which is the tsunami force expected at the building site and also the maximum inundation depth. So thanks to the VDPO BI analysis, we can define the activity curve for the structure, like we do for seismic during the seismic assessment, assess the damage to structural and non-structural components during the inundation, and also check if the structure is able or not to sustain the tsunami demand at the specific location, given this a specific kind of tsunami inundation scenario. Then we can, when we have a methodology and tools for perform a refined assessment of the performance of a structures, then we are able to design also retrofit intervention that can be able to avoid the damage of such structures without, in the optic of sustainability. So sometimes the retrofit is not a viable choice, and we don't have any other alternative except from the demolition and reconstruction. But in the perspective of sustainability, we always try to reuse existing structures and try to adequate their performance to our current standards. Okay, so basically retrofit systems for reinforced concrete existing structures are a lot on different structural needs, and most of them are very well known in the construction practice, and also their effectiveness has been proved, is well assessed, and has been proved also by past event and disaster, like this picture taken after the Central Italy earthquake in 2016, where we can see the perfect effectiveness of the FRP strengthening of this part of the building that is still standing after the earthquake. The research is also currently focusing in developing new technologies that, other than respond to the safety level, increasing the capacity of members, looking also at the other aspects of durability and sustainability. And in this perspective, we are working on the adoption, for instance, of inorganic composite materials that sometimes can be more sustainable given the low amount of polymers inside the matrix, like high and ultra high performance fiber reinforced cement composites, for instance. In this case, we have I will not say much more on this aspect because I discussed already of this technology during a previous FIB webinar that you can now find on the YouTube channel of the FIB. And there are also other kind of retrofit solution with inorganic composite materials like FRCM technology, TRM, and so on. And we have also the new trend. The new research is now looking at the adoption of smart materials, like, for instance, shape memory alloys for strengthening and retrofit existing structures. And also on this topic, we had a webinar a couple of weeks ago. So if you're interested, you will find the video on the YouTube channel in a couple of weeks. And seismic retrofit solutions are well known, and they are used both for increasing the capacity of structural components like beams, columns, shear walls, and also beam column joints in different of course, solution and technologies. And also are adopted commonly for preventing the damage to non-structural components, so increasing the measure infill walls both from their in-plane direction, and also to prevent the out-of-plane overturning, out-of-plane failure. And also in this case, avoid also danger for human lives. And retrofit solutions for other kind of hazards are less investigated, less known, but definitely we can say that they can exist, and we are working on this too now. We are looking at extending the perspective of retrofit also to other kind of hazards. When we talk about tsunami, the current approach, the most diffused, is a large scale countermeasure approach against tsunami. And it consists in the adoption of physical barriers like seawalls or mangroves that dissipate the energy of the tsunami offshore and then decrease the velocity of the inundation depth and the flow when these arrives on shore. So this is less destructive when it arrives on the coastal communities. But retrofit solution at single building level can also be developed and tailored. Of course, the adoption of retrofit solution can be definitely adopted for definitely adopted for critical infrastructures and like hospitals, for instance, or for buildings can be adopted as tsunami vertical shelters, and also, of course, for those buildings that can be considered as have a cultural heritage value and so need to be saved for future generations. So here are some examples of which kind of intervention can be needed for tsunami loads. We can strengthen the columns and the elements at the ground story level to avoid the damage from lateral loading and from debris. But we can also think to systems to avoid damage caused by the buoyancy, in this case with breakaway slab systems, for instance, or with the adoption of deep foundation, so to avoid the effect of overturning observed in a previous tsunami. And also intervention on the foundation can be helpful in the case of damage due to scour, so preventing the soil erosion or avoiding local collapses, also increasing the redundancy of the structure when it is possible. In general, when we design retrofit solution, we also need to think of the effect that kind of retrofit solution will have of sequential events. So in the case of earthquake followed by tsunami, we need to consider that any kind of intervention that we do for the seismic strengthening will affect also the response under tsunami. And this is an example, for instance, of a bridge that was strengthened for resist to earthquakes. So the piers were jacketed in this case. And after the 2011 tsunami, the pier was completely undamaged. So basically, this kind of strengthening solution designed for seismic as a seismic intervention actually helped also during the tsunami event. And also the use of jackets with materials that can enhance the durability will be also helpful during a tsunami because, of course, if you consider reinforced concrete members that will completely submerged in the seawater, of course, will be subjected to a faster rate of corrosion and degradation caused by this stronger attack of chlorides given by the seawater. And also in terms of strengthening of out of plane of non-structural components like the infills, the strengthening of out of plane, strengthening to prevent the out of plane failure of the infills can be important, especially for critical infrastructures, structures with valuable contents, and also shelters. And it will also reduce the generation of debris. That is another issue that we've seen. The management of debris is also another aspect to be considered. But we should also be careful because sometimes this can be detrimental, because if we remember that the loading acting on structures is a function of the surface closer to the flow, so to the water. Of course, the adoption of systems that prevent the failure of the infill walls will make our structure like waterproof. And so in this way, we will increase the loading acting on structural members. So if we see at these performance curves derived by the VDPO VI analysis, we see that actually the structural capacity will be decreased by this intervention on the exterior claddings. And so maybe another additional strengthening solution for columns, for instance, will be necessary to allow the structure to sustain the tsunami-induced loads. Of course, this field needs to be further explored, and many challenges related to tsunami and also other kind of hazards still remain open, both regarding the assessment and also the retrofit. So if you have any idea or proposal for discussion, please feel free to ask questions or to contact me. And many thanks for your attention, and apologies for the connection.
Thank you very much. Marta, you did a good job taking that into account, and we could see most of your presentation. Andris Setiowan, in majority of the events, earthquakes happens before the tsunamis. Does the performance-based assessment methodology that you propose for the tsunami considers also this multi-hazard interaction?
Yes, this is a very good question. And actually, this is one of the challenges that we are addressing. Methodologies to account for this interaction has been developed. There is a paper from Professor Rossetto about the double pushover methodology, or in general, performing nonlinear dynamic analysis before for the seismic assessment of damage, and then after that, performing the VDPO VI analysis can be definitely an approach to consider the preceding damage of earthquakes in the tsunami response. So this is for sure an aspect that we need to consider when we perform the assessment for these sequential hazards and events.
Okay, there are some questions in the chat, but we will have no time to answer those. I will ask Marta maybe to answer some of them directly to them later on. Thank you very much.